A control system that performs just fine on a laboratory test bench may not work at all in the real world. In the lab, the cable runs are short and the electrical noise is minimum. The real installation may require cable runs of perhaps hundreds of feet in a dirty, electrically noisy environment. In this section, we will examine some of the problems and their solutions in the area of signal transmission. Earth-ground refers to an electrical connection to the surface of the earth, usually through a metal rod driven into the ground. Because the earth is not a particularly good conductor, the ground voltage is different from place to place. Often confused with the earth ground is the signal common or signal return, which is a conductor in the circuit and serves as a common reference point for all the other circuit voltages. The signal common of a circuit is often referred to as the ground, and it may or may not be connected to the earth ground. For a DC circuit, the signal common is usually connected to the negative terminal of the power supply or the battery. An automobile chassis ground is the example of this. AC signals also have a designated signal return. With the exception of antenna systems, circuits do not have to be attached to the earth to work, but most are. This is done primarily for safety reasons so that high voltages cannot build up between the chassis and the local ground. Consider the situation illustrated in Figure A. A 200 volt AC signal is generated in one unit and sent by two wires to a second unit. The signal common is connected to the chassis, but the chassis is not connected to the ground. This circuit would work fine electrically, but there is a potential safety hazard. Due to inductive and capacitive coupling, it is likely that the 200 volt signal would align itself as shown, plus 100 volts for the signal and minus 100 volts for the signal common and chassis. This is dangerous because anyone standing on the ground and touching the chassis would get a 100 volt shock. In Figure B, the chassis has been connected to an earth ground. Now the voltage of the chassis is 0 volts with respect to the earth and is safe to touch, as is the signal common wire. This is a very simplistic view of quite a complicated subject, but it gets the concept across. Sometimes both the source and the receiver are earth grounded, as shown in Figure A. One might be tempted to use the earth as the return path, but this won't work because the earth is not a good conductor, and probably the two ground points are not at the same voltage. Assume that the cable in A is 200 feet long, and the source voltage ranges from 0 to 2 volts. The difference in earth voltage for that distance could easily be 3 volts due to local conditions. It is a case where the noise of 3 volts is larger than the signal of 2 volts. Connecting a separate signal return wire, as shown in Figure B, is not a good idea because we now have a ground loop. Ground loops occur when large currents flow in the return wire because of the difference in ground voltages. In the circuit in Figure B, the wire resistance is 0.3 ohms for wire size of AWT gauge 12, and if there really is a 3 volt difference between the two ground points, the ground loop current would be 3 volts over 0.3 ohms or 10 amps. Clearly, it is not desirable to have large, unpredictable currents running through your cabling. The solution to the ground loop problem is indicated in Figure C. The circuit shows that a return wire for the signal is added, but it is grounded only at one end. The ground loop problem can be avoided by simply not connecting both ends of the signal return to an earth ground. However, sometimes the ground connections have already been made inside the equipment, in which case the only solution is to use isolation circuits between the source and receiver. An isolation circuit can transfer a signal voltage without any metal-to-metal contact. This allows for the signal common of the source to be at a different voltage from the signal common at the receiver. There are two main types of isolation circuits: transformer coupled and optical coupled. We will now look at both isolators. This diagram shows a transformer-coupled isolation circuit. The input voltage is used to amplitude modulate an internally generated AC voltage. The modulated AC voltage is transformer-coupled to a demodulator, which reconstructs the original input voltage. The modulation is necessary because most sensor outputs are slow-changing DC and not AC. Because there is no electrical connection across the transformer coils, the signal commons can exist at different voltages, and the ground loop path is broken. Linear optical isolator. The input signal is amplified to drive a light-emitting diode, or LED. A phototransistor receives the light signal and converts it back to a voltage. Isolation is achieved because the input and output are two separate circuits with no electrical connection. To ensure that the output is an exact copy of the input, a feedback system using a second phototransistor is incorporated. A simpler optical device can be used if the signal to be isolated is digital. Digital signals do not require a linear relationship between input and output. They are just on and off. The diagram shows a typical digital optical coupler. A standard TTL digital device can drive the input. When the input Vin is driven low, a voltage is developed across the LED, causing it to light. This light turns on the phototransistor, which pulls its output Vout to 0 volts. The output of the photocoupler can be connected directly to a TTL gate with a pull-up resistor as shown. Optical couplers, sometimes called optoisolators, are very useful in providing noise isolation because signals can only travel in one direction through the coupler. Shielding from magnetic field noise. A current through a wire generates a magnetic field around that wire. If another wire happens to be in the vicinity, the magnetic field from the first wire will induce a current in the second wire proportional to the rate of change of the magnetic field. Therefore, DC will not induce current in a nearby wire, but AC will. This undesired induced current is called electrical noise. Good design practice dictates that wires with large AC currents, such as 60 Hz power wires, be kept apart from low-level signal wires. Shielding cannot block the magnetic field noise, but it can draw it away from the signal wire. This is shown in a cross-sectional view. A shielding material is used that has a low resistance to the magnetic field. For this application, steel is better than copper or aluminium. The magnetic lines of force are more inclined to go through the shield than the air, so the field within the shield is sharply reduced. For this to be effective, the shield must be relatively thick-walled, and in fact, even a heavy conductor placed near the signal wire will act as a magnetic shield. Another source of noise is from an electric field. An isolated wire placed in an electric field will assume a voltage proportional to that field. Figure A shows a wire in the middle of a 100-volt field. The wire will assume the voltage of 50 volts. If the field voltage is AC, then the AC voltage will be induced on the wire. Large, time-varying electric fields are common in an industrial environment. Merely putting a conductive shield around a wire will not keep the field out. As Figure B shows, the shield itself would acquire a voltage from the field and then re-radiate this voltage to the wire. However, if the shield is grounded, forced to be 0 volts, then there can be no electric field within the shield, and the wire is protected in Figure C. For best results, the shield should not be used as the signal return path because the shield will probably have noise on it from the shielding action. The ideal setup is shown in Figure D, where both the signal and the return are contained within a shield, and the shield is grounded at one end. Shield grounding considerations. The time to think about grounding is when a system is being designed. A grounding strategy built in from the beginning is better than trying to patch things after the system is built. We have discussed the fact that shields must be grounded to be effective and that they should be grounded at only one end. Because the controller is the hub of the control system, it makes sense to tie all shields together at the controller and ground them there. This is called a single point ground and is illustrated in Figure A. It is important that the single point ground have a solid, low impedance connection to a real earth ground. Otherwise, noise coming in on one shield will re-radiate out on all the other shields. Sometimes the shield cannot be isolated from ground and the component end. In such cases, the best approach is to insert an isolation circuit and break the shield at that point, as shown in Figure B. This approach has the advantage of allowing individual components to be grounded for safety reasons, yet preventing ground loops. Now let's look at some practical wiring considerations. Most electrical wires are made of copper because it is one of the best conductors available, being both cheap and having good conductance, but even copper has some resistance. This resistance can usually be ignored for small currents and short runs, but for longer runs and bigger currents, wire size becomes an issue. The thicker the wire, the less resistance it has, so a thicker wire can carry more current than a thinner wire without heating up, and there will be less voltage drop along its length. Wire size is specified by the American wire gauge AWG as shown in this table. Notice that as the AWG gauge gets bigger, the diameter gets smaller, and the resistance in ohms per 1,000 feet goes up and the current capacity goes down. Generally speaking, there are two categories of wire usage: power and signal. Power wires supply electrical power, for example, to drive larger motors. And signal wires are used for communication, for example, to connect a limit switch or a temperature sensor. Power wires tend to be in the range of 4/0 to 14 gauge, depending on the current capacity required. So 4/0 comes from saying 4 noughts. So that's the hash 0000. So that's 4 noughts or 4/0. Signal wires tend to be in the range of 18 gauge to 28 gauge, depending on the voltage drop that can be tolerated. As explained earlier in the chapter, sensors that use the current loop technique are immune to voltage drop problems, so wire size is usually not an issue. However, sensors that output a voltage signal have to be concerned with volt drops in the line. Let's take a look at wire size examples. In this example, a temperature sensor connects to a controller 100 feet away using 24 gauge wire. The sensor puts out a voltage from 0 to 10 volts, and the controller has an input resistance of 1 kiloohms. What will be the maximum voltage drop along the wire? Let's have a look at the solution. First, calculate the resistance of the wire. From the wire table, we see that 24 gauge wire has a resistance of 25.67 ohms per 1,000 feet. The total length of the wire is 200 feet, 100 feet out and 100 feet back. The total resistance of the wire is thus 25.67 ohms divided by 1,000 feet, multiplied by the 200 feet length, and we get 5,13 ohms. From Ohm's law, we know that the voltage drop is proportional to current, so we need to determine the maximum expected current in the wire. That will occur when the sensor is putting out 10 volts. Note the circuit resistance is the 1 kilo ohm load plus the wire resistance. So the maximum current in the wire is V over R, or 10 volts, divided by 1000 plus 513 ohms. And that comes out at 9.95 milliamps. Knowing the current, we can calculate the voltage drop along the wire using Ohm's law. Voltage drop along the wire is equal to I times R, or 9.95 milliamps, times 5.13 ohms, which is equal to 0.05 volts. So, in this case, the total wire voltage drop is only 0.05 volts, which is 0.25 volts out and 0.25 volts back, leaving a signal voltage at the controller of 9.95 volts. Power wire is available as individual insulated wires, as shown in Figure A, or in pre-made cables. Probably the most common power cable is the non-metallic sheath copper cable shown in Figure B, which is available in sizes 2 to 14 gauge. You probably recognize this as a standard house wiring cable. Larger power wire is available as service entrance cable. See Figure C. This cable is available in sizes 4/0 through 8 gauge, usually as stranded copper or aluminium. Signal wire is used to connect sensors, switches, and small motors, as is typical size is 18 to 24 gauge. This wire usually comes in pairs that are twisted together, and it may or may not be shielded. Twisting the wires not only keeps them together, but also reduces interference problems. Shielding further reduces susceptibility to interference. A typical twisted shielded pair is shown in Figure D. The sheer number of cables in an automated industrial setting requires some organization. The individual wires that go out to a sensor or limit switch may just be tied or clipped to whatever superstructure is handy, but at some point in the system, multiple cables going in the same direction will be grouped in a cable tray or electrical conduit. The first rule is to put power and signals in separate trays or conduits, if at all possible. And if they must cross, they should cross at right angles. Even if the signal wires are in a continuous metallic wireway or conduit, they should be kept at least 3 inches away from AC power lines with up to 20 amps, and at least 6 inches from AC power lines with more than 20 amps. If the signal wires are not in a metallic conduit or tray, the separation should be doubled. This was a brief introduction to signal transmission. The point was to highlight some of the issues to consider when transmitting signals. There is certainly a lot more to consider, but as long as you are aware that there are issues to consider, you will be reminded to research these issues prior to starting your design. Despite this knowledge, it is surprisingly common to find projects delayed at commissioning stage because earth bonding, shielding, and signal attenuation were not dealt with in the initial design.